summer with Nicole, and today she'll tell us about your project together, Illuminating the Invisible, measuring oxygen-6 gas in the circumgalactic medium of simulated.
Hello everyone, thank you Gwen for the introduction. So for my project this summer at Carnegie, I used computer simulations of galaxies to improve our understanding of galaxy evolution. So observers have found that almost every galaxy in the universe has a supermassive black hole, indicating that supermassive black holes are fundamental components of galaxies. There's an interesting relation that is called the M sigma relation, which shows a strong linear relationship here connecting the mass of the supermassive black hole and the velocity dispersion of the host galaxy's bulge. Sigma here refers to the velocity dispersion, which is like the differences in the random rotation of stars within the bulge of a galaxy. So this further indicates that galaxies and their central supermassive black holes co-evolve. But astronomers don't fully understand this coevolution, which is why a big question is what is driving this connection? One way that galaxy evolution and supermassive black hole growth is connected is through a process called feedback. Supermassive black hole feedback is the energy that comes from the very hot and bright accretion disk around the black hole, which can eject gas from the center of the galaxy out into the galaxy's halo. And the halo of gas that surrounds the galaxy is known as the circumgalactic medium, which extends from the edge of the galaxy's disk out to the outer boundary of the dark matter halo. The circumgalactic medium plays a critical role in galaxy evolution as it hosts the inflows and outflows of gas, which can affect a galaxy's chemical composition, morphology, and star formation rates. These outflows of gas that you can see here are potentially due to feedback processes, which can warm and heat and move gas from the center of the galaxy out into the circumgalactic medium. But since the circumgalactic medium contains such a low density across a vast distance, observers use quasar spectroscopy in order to probe the diffuse gas around the galaxy. And one ion that's been observed are O6 ions, which are considered a useful tracer for this warm hot gas. And by O6 ions, I'm referring to oxygen atoms that have been stripped of 5 electrons, meaning that they are highly ionized and that it took a large amount of energy to do so. Indicating that the O6 content can be seen as like a thermometer for the temperature in the halo. So O6 ions help us understand the properties that make up the circumgalactic medium, and they are also used to explore the impact that supermassive black hole feedback energy has, since the process heats up the surrounding gas. O6 ions have been measured by many observational surveys of real galaxies in the universe. This data plot here shows observational data obtained through quasar spectroscopy of real galaxies in the universe that I will be comparing my simulated data to. So I'm using the Romulus 25 simulation, which is a high-resolution cosmological simulation that has well-tested gas, stellar, and supermassive black hole physics. From this simulation, we selected a sample of 911 galaxies that fit the parameters and match the criteria of the data plot that was shown previously. So with that in mind, and by using the Romulus 25, we question, do our simulated galaxies accurately produce the expected O6 content observed in the circumgalactic medium of real galaxies in the universe? Here are a few examples of the galaxies that are within my data selection. So we have H19 here, which is a spiral galaxy, H25, which is an elliptical galaxy, and H333, a dwarf galaxy. I also plotted the star formation history plots, which can show us events that have affected or impacted star formations, such as quenching or mergers. I also plotted the gas density and temperature for each of the galaxies and printed the stellar masses here, just so that you can see that my data selection contains a range of different stellar masses. One thing that I would like to point out here is that the circumgalactic medium is known to have a reservoir of multi-phase gas, meaning that it contains varying densities and temperatures. So if you look closely here at these plots, you can see that there's like lower temperature here, but higher temperature here, and then also in the density as well, you can see these like little random areas of higher density in like a low density area. But in order to calculate the amount of this warm hot gas specifically traced by those O6 ions, I have defined the circumgalactic medium within my galaxy simulation as all of the gas that is inside the virial radius of the halo down to the edge of the galaxy's disk that is about 10% of the virial radius. So here just shows all the gas particles that are outside the galaxy's disk but inside that virial radius. This is the equation that I use to calculate the total amount of O6 gas in the circumgalactic medium of my simulated galaxies. So we have m gas here, which is the mass of every particle. F oxygen mass is the fraction of gas particles in oxygen, and FO6 mass is the fraction of oxygen mass in O6. So with my results, I then plotted the total O6 mass against the stellar mass from all 911 galaxies from my Romulus 25 simulation. And you can see this like clear linear trend here. But you can also notice that there's no like deviated points above this trend. There's only some that fall below it. This could potentially be due to events that have disrupted the gas in the circumgalactic medium, such as like tidal stripping. These orange markers that you see here are simulated data points from Pichatelli, who used the same code but at a higher resolution. This highlights that at the lower stellar mass end, or like towards the dwarf galaxies, that my calculations for the total amount of O6 are well aligned with simulations that have a higher resolution, despite Romulus 25 lacking metal cooling physics. But in order to compare my simulated data to the observational data plot, I then calculated the column density using this equation here, where these top variables are the same from the previous calculation. But MP stands for the mass of the proton in grams, and the bin size refers to the size of the bins used to calculate the profile. So in my simulation, I calculated the column density profile using this equation and then took the average of the profile within each galaxy, which is consistent with the observational analysis, so that I can compare both data sets. So with my results, I then plotted the average column density against the stellar mass from my Romulus 25 sample. Again, you can see that clear linear trend up here, but this time it has like a definitive peak at about 10 to the 10 solar masses before it starts decreasing downward. But if you take a look at the lower lower stellar mass range at 10 to the 7 to 10 to the 8 solar masses, you can see like this scattered deviations, scattered deviated plots over here. As of right now, we are still uncertain of what's causing that to happen, but we plan to investigate that further. Here just shows both of my simulated results with the total amount of O6 gas in gray here and the average column density in blue here. And this just highlights that if you look at the higher stellar mass range, the total amount of O6 continues to trend upwards, while the average column density peaks at 10 to the 10 solar masses before it starts decreasing downwards. So the main takeaway here is that the shape of the column density relationship is different than the total amount of O6, meaning that the column density does not fully capture the total amount of O6 in the circumgalactic medium of high stellar masses. And then if I were to zoom into the higher range in the column density, I would be able to better compare my results to the observational results. So here shows the red and gray markers that represent the mean and median from the data plot along with their error bars. And if you take a look at the higher stellar mass range, you can see that my simulated results are well scaled with the observational results. Here's a better view of the two plots like side by side. And if you take a look at the lower mass range, you can see that my simulated average column density is a little bit too low to match for the observational data. This discrepancy may be due to how we define the virial radius, and if we extended our measurements for dwarf galaxies to about 2 RVR, then maybe this could potentially get my simulated measurements to properly scale with the observational measurements, but that is still something we're also looking into. So the main takeaway here is that the column density from Romulus 25 are consistent with the observations of column density, meaning that the amount of warm hot gas in our galaxies are comparable to observations. So now that we know that my simulated results are well matched with the observational results, we plan to further investigate what is we plan to further investigate like the process that is driving the warm hot gas into the circumgalactic medium and potentially connect it to the impact that supermassive black hole feedback has on its host galaxy. So to take this project a step further, we then asked, does the amount of O6 in the circumgalactic medium of galaxies trend with supermassive black hole feedback? So I'll leave my takeaways up here, and I'm happy to take any questions. Thank you.
Thank you for this amazing presentation. My question is, are these galaxies assumed to be local galaxies?
That's a good question. I'm not entirely sure if they're considered local galaxies. For my data set, we were just looking at galaxies that range from different stellar masses to like broaden like the data points from my mentor who looked at Milky Way scaled galaxies. So I'm not entirely sure if they're local galaxies, yeah.
And the ones you're comparing them with?
Again, I'm not entirely sure. Yeah, I'm sorry.
More questions? So it's really wonderful to see ACGM results. This is really exciting. I'm sort of curious if like all of the systems, even at these sort of lower masses, have kind of the same black hole feedback that's in Romulus, and so you're planning to kind of look at sort of the full mass range in the future?
Yeah, that's a great question. So previously, supermassive black hole or just black hole feedback in general wasn't really looked at in dwarf galaxies until recently. And there's a lot of data that's showing that there is feedback processes. So I'm hoping that with this data and now knowing that these observations are matching, or sorry, now knowing that my simulations are matching the observations, that we can start looking into what causes that discrepancy in my simulated results and further explore if it's due to feedback processes. Yeah.
Wonderful. Let's thank Julia again.